Welcome to a lesson on solving a first-order homogeneous differential equation written in differential form. A first-order differential equation written in differential form, as we see here, is homogeneous if function m and n are homogeneous functions of the same degree, which means we're going to find m of tx comma ty and n of tx comma ty and make sure we can write them both as t raised to some power times the original function, and in both cases the exponent on t must be the same in order for the functions to be homogeneous and therefore the differential equation to be homogeneous. So once we determine if the first order DE is homogeneous, we can solve it by performing a substitution. And we have two options for the substitution. We can let y equal x times v, which means differential y would be equal to this, using implicit differentiation and the product rule, or we can let x equal y times v, and therefore dx would be equal to this, again using implicit differentiation and the product rule. To decide which substitution to do, we're going to look at the original differential equation and determine whether m or n is simpler. If m is simpler, that means we want to perform a substitution for dx, and therefore we'll let x equal y times v. If n is simpler, then we'll perform a substitution for dy, and therefore we'll let y equal x times v. Once we perform the substitution, we can solve the resulting dE using separation of variables, and then we'll solve the original dE in terms of x and y. So let's take a look at our first example. The first step is a test to see if this is homogeneous. So we need to recognize that function m of x comma y equals x minus y, and n of x comma y would be equal to just x. So now we'll find m of tx comma ty, which would be tx minus ty. Notice if we factor out the t, we have t times x minus y, which means this is equal to t times the original function m of x comma y. So because this is t to the first, m is a first degree homogeneous function. And now we'll determine n of tx comma ty, which will just be t times x, which we can write as t times the original function n is equal to x, so this is t times n of x comma y. Notice how this is also t to the first times n. Notice both m and n are degree 1 homogeneous functions. Therefore, the original differential equation is also homogeneous, which means we can solve it by performing a substitution. Let's perform that substitution on the next slide. Notice that here function n is simpler than function m, so we want to perform a substitution for dy, which means we're going to let y equal x times v. Therefore, differential y is going to be equal to x times dv plus v times dx. Here we applied implicit differentiation and the product rule. Now we'll perform the substitution. So we'll have x minus y, which is equal to xv, times dx, plus x times dy, which is x dv plus v dx. And this is all going to equal 0. Notice now our differential equation is in terms of x's and v's. Let's go ahead and clear the parentheses and simplify. So we'll distribute here. We're going to have x dx minus xv dx plus x squared dv plus xv dx. Notice how here we have minus xv dx, and here we have plus xv dx, so this simplifies to 0. Now we want to solve this using separation of variables, and since this term has dv, we'll subtract it to the other side. So we'll have x dx equals negative x squared dv. We want all of the x's on the left side, so let's go ahead and divide both sides by x squared. So now we would have 1 over x dx equals, this would be negative dv. Now we're going to integrate both sides of the equation. We'll go ahead and factor out the negative, so the integral symbol will be here. So we'll have the natural log absolute value of x plus our constant of integration is going to be equal to, this would just be negative v. We would have another constant of integration here, but we already put a constant on the left side of the equation. Let's go ahead and finish this on the next slide. Remember, our goal is to solve this in terms of x and y, so we need to perform a substitution for v. Remember, we started with the substitution y equals x times v, which means v is equal to y divided by x. So we have natural log absolute value of x plus c is equal to negative y divided by x. Now we'll go ahead and multiply both sides of the equation by negative x. So we'll have negative x natural log absolute value of x minus c times x equals y. Or if we want, we can switch this around. Y equals negative x natural log absolute value of x minus c times x. This would be the general solution to the original first order homogeneous differential equation. Let's finish by taking a look at this graphically. Here's the original differential equation. We can use this to create the given red slope field below, and then given our general solution, if we select values of c, for example, c equals negative 2, negative 1, 0, 1, and 2, we can graph some of the solutions from the family of solutions, so every graph below represents a possible solution to the original differential equation. Okay, I hope you found this helpful. We'll take a look at another example in the next video.